exact equations. This is going to pull together all our other methods for first order equations we've been doing, because if you really think about it, all the equations so far that we've done, you're trying to get the equation into some form that you can integrate it. That's what an exact equation is. It's an equation that's an exact differential equals 0. You write it as m dx plus n dy equals 0, or this is d of something, and so you integrate it and find out what the solutions are, at least implicitly. All the other methods boil down to being able to do this. So what's an exact equation? It's an equation, a function of x, y times dx plus a function of x and y times dy equals 0, where m is the derivative of some function phi with respect to x, and n is the derivative of the same function with respect to y. If you can put your equation in this form, then all you have to do to solve it is integrate it. How about that? So it's an easy method, but the trick is you just have to get lucky to be able to put it in this form, So here's the notation. When I want to put a partial derivative with respect to x, I'll write df dx. Some people have been asking, when do we use partial derivatives in this course, because they know it's coming. Right now is the main time, although we did a little bit in the existence of uniqueness theorems. Fx will denote partial of f with respect to x. Fy will denote partial of f with respect to y for a function of two variables, x and y. And then what we just said, a differential form, m dx plus m dy is exact, or a total differential on an open region R of the xy plane, if there exists a function phi such that m is partial of f of phi with respect to x, and n is the partial phi with respect to y. We'll use this shorter notation now. A first order differential equation equals this, m dx plus m dy equals 0 is said to be exact if it's an exact differential equals 0. The exact differential is one that can be integrated. For this reason, you rewrite the equation as d phi dx dx plus d phi dy dy, just because m and n were these things. And then this is d of phi, right? If you use the chain rule as d phi dx dx plus d phi dy dy is d phi, so you rewrite this as d phi equals 0. You integrate it, and the solutions are phi equals c. In other words, any function y of x, which is a level curve of phi, in other words, if phi equals a constant, is a solution. So this implicitly determines solutions along all portions of these level curves of phi of x, y that make y a differentiable function of x. Well, to determine if an equation is exact, how do we know? We look at it, it may be hard to figure out which function phi has this derivative, which function phi is such that n is the derivative of it with respect to x, and n is the derivative of it with respect to y. So here's a test. On an open, simply connected region R, which will be for us all the time, all right? On which m and its first partial derivatives are continuous, and n and its first partial derivative is continuous also. It turns out, you remember this from calculus, the end of calculus, this differential will be exact if and only if partial of n with respect to y is equal to partial of n with respect to x. All right? This is the reason you should remember this is if m is d phi dx and n is d phi dy, then this is phi xy, and this is phi yx. This is saying the second partials of phi are equal. So this will be an exact differential if and only if ny equals nx, in which case these are the phi xy and phi yx are equal by calculus, the end of calculus. Now, consequently, we have this theorem. If on an open, simply connected region R with m and its first m and n and their first partial derivatives continuous, my is equal to nx and n not equal to 0, then a dE of this form, m dx plus n dy equals 0, is exact by their theorem from calculus. So a function phi exists such that m is phi x and n is phi y, and the solutions to the differential equation all satisfy phi of x, y of x equals a constant. All right, so this is what we can do. How can we find the solution? Well, m is supposed to be the partial derivative of phi with respect to x, right? So how can we find it? Phi, if m is its derivative, we just integrate, right? So phi must be the integral, partial integral of m with respect to x. Similarly, since n is the partial of phi with respect to y, phi must be the partial integral of n with respect to y. These are partial integrals treating the other variables as constants. So you treat x as a constant when you do this integral, treat y as a constant when you do this integral. And then both of these give you phi to within an arbitrary constant that since you treated x as a constant in this integral, the arbitrary constant in this integration can be a function of x. The arbitrary constant in this integral can be an arbitrary function of y. Since it's a partial integral, between these two you can figure out what phi is what the point is. That needs a little more explanation. We'll do it with an example here. And then we said curves that are differentiable functions along phi of x, y of x equals c are implicitly determined differential equation solutions. So let's try and find the solutions. We'll find a one parameter family because the arbitrary constant that comes in will be the parameter. We'll try and find all solutions that we can of 2x plus y dx plus x dy equals 0 by integration. Once in a while there are other solutions called singular solutions that aren't determined by integration, so this doesn't necessarily get all solutions, but we'll find all of them that we can by integration. Find an interval on which it's unique. We can appeal to the existence of uniqueness theorem. Well, here it is. 2x plus y dx plus x dy equals 0. This is m in the theorem, and this is n in the theorem. So how do we check if it's exact? We see if partial of this with respect to y is equal to partial of this with respect to x. So here's m and here's n. But partial of m with respect to y is 1. Partial of n with respect to x is 1. They're equal. This is an exact equation. This must be the derivative with respect to x of some function, and this the derivative with respect to y of the same function. What must it be? We use partial integration. We integrate m with respect to x, and we get, well, what's partial of, we're taking the integral of 2x plus y, integral of 2x with respect to x, partial integration treating y as a constant is x squared. Partial integral of y is just x times y, right? Because we're treating y as a constant. Integrate k, you get kx, but k is really y. And then there's an arbitrary constant. But since it's a partial integration, the arbitrary constant can depend on y, so we say plus an arbitrary function g of y. Similarly, phi must be the integral of n, whenever it multiplies dy, with respect to y, treating x as a constant. So we integrate x with respect to y, we get xy plus an arbitrary constant. Since x is treated as a constant, and here this can depend on x, we get xy plus an arbitrary function of x. So there's what we know by integrating this with respect to x. We know the phi must be of this form. By integrating this with respect to y, we know that phi must be of this form. We know from the theorem, since my equals nx, that these two can are equal for some g of y and f of x. We just have to figure out what they are. How can these be equal? Well, the xy term matches. This one's missing an x squared, but that can go into f of x. Then, these both have x squared plus xy, and so g of y is left over, can't depend on either x and y since everything else matches. Must just be a true constant, not depending on either x or y, and that can be included in f of x over here. So this is x squared plus c, and this is c, and then these two are equal. That's the only way you can make them equal. So phi must be x squared plus xy plus c, where c is an arbitrary constant. All right. Now, this generates what we call a one-parameter family with c the parameter. Just meaning the parameter is an arbitrary constant is what we mean. And accordingly, a one-parameter family of integrated solutions is phi of xy equals a constant capital C, let's say, right? That's what the theorem said. If you find phi such that the left side of the differential equation is d phi, then the solutions lie along curves phi equals a constant. So I'll use capital C here. And so I set this equal to an arbitrary constant. What I have is, well, you can solve for this. We can put the little c and the big C together actually here. And we'll say x squared plus xy equals c is the family of solutions, implicitly the family of solutions. If you divide through by x squared plus x, you get y equals c over x squared plus x, which can also be written this way. Oh, I'm sorry, I didn't write that right. I'm sorry. It's c minus x squared all over x. Comes out to be y equals c over x minus x, with c arbitrary. Here is for all the integrated solutions we can get. Now, in this problem, I also said, suppose we have an initial condition, y of 1 equals 0. In other words, when x equals 1, y equals 0. All you have to do is plug in x equals 1 in here, and you get 1 over x minus 1 minus x equals 0, should have been. Let's see. Oh, I'm sorry, this is the solution. Plug in x equals 1, y equals 0, you get 0 equals c over 1 minus 1 added to this. So c must be equal to 1, and that provides this solution, putting in c equals 1. Y equals 1 over x minus x is the unique solution to the initial value problem. How do we know there's not some other singular solution? I talked about there could be extra solutions. The existence of uniqueness theorem guarantees that through this point there's a unique solution. So we don't have to worry about maybe there's another solution here. Just a comment here. This particular equation we could have solved another way. We could have rewritten it as dy dx plus 1 over xy equals minus 2 and solved it as a linear equation that way also. And the theorem for linear equation guarantees that there's unique solution actually on 0 to infinity. All right. Here's a geometric interpretation of this. Suppose we want to solve this differential equation, dy dx equals x squared minus 2y over 2x minus y. We don't have a method for this. It's not homogeneous because these are different powers here. We can't write it as a function of y over x. It's not a Bernoulli equation, but it's not a linear equation. It's not reciprocal as linear, I don't think. It's not separable. All our other methods fall this time, but maybe we'll get lucky, right? This is the method of being lucky. If I multiply this through by 2x minus y dx, I get this when I write it in the form of a differential equals 0. 2y minus x squared dx plus 2x minus y dy equals 0. So given this equation, I rewrite it in this form. And I notice I'm lucky, it's exact. Partial of this with respect to y is 2. Partial of this with respect to x is 2. The two are equal. So partial of this with respect to y and then partial of this with respect to x are equal. Then this is the derivative with respect to x of some function. This is the derivative with respect to y of the same function. We can just do partial integrals of this with respect to x, of this with respect to y. And we get in the first case 2x y minus x cubed over 3, treating y as a constant, plus an arbitrary function of y. Treating x as a constant and iterating this, we get 2xy minus y squared over 2, plus an arbitrary constant, which is an arbitrary function of x, since x was treated as a constant. Now how can we make these two equal? Only if this goes into g of y and this goes into f of x, and we get minus x cubed over 3 minus, let's see, plus 2xy, the thing they have in common, minus y squared over 2, plus an arbitrary constant can be in there. So we can put a plus c on here. Nothing wrong with that, but I won't bother to put it on this time. Why not? Because regardless of whether we put a plus c in there and get all functions such that m is the partial with respect to x and n is partial with respect to y, all we need is one of them. We set any one of them equal to a constant, we get all solutions. So here it is. We'll choose c equals 0 in this one and then set phi equal a constant to get all the solutions. And now we can rewrite this by subtracting the c over and regrouping as 1/2 y squared minus 2xy plus x cubed over 3 plus a constant equals 0. and say, all right, this gives the solutions implicitly through integration. These are level curves, often they're closed curves or something. It doesn't determine y as a function of x. How can I determine the actual solutions, right? Solutions are y as a function of x that's differentiable along the interval. Well, I just have to solve for y. Notice this is ay squared plus by plus c equals 0. I can solve it by the quadratic formula. Right? It's minus b plus or minus square root of b squared minus 4ac all over 2a, which is 1. And these are the solutions. One solution for the plus, one solution for the minus. This is solutions in pairs, one solution for each c also. So there's an infinite number of solutions with the plus and arbitrary c, and there's an infinite number of solutions with the minus and arbitrary c. And these fill up the xy plane with solutions. Here in this section we've written y as a function of x, where in previous sections I wrote y as a function of t, because these are real nice to plot in the xy plane. So it's kind of nice to use x and y instead of t and y here. And figure 230 displays what's going on here, which is kind of neat if you're a geometer. I like this interpretation of it. What you do is you take the exact differential m dx plus n dy and you integrate it and you get a function phi of xy, right? Here's the plot of z equals phi of xy. It's a surface. Remember that from calculus 1, calculus into calculus. You plot z equals phi of xy as a surface over the domain of phi. Here's the surface that we had for this phi that we integrated to get. Now what is a solution to an exact differential equation? It's the level curve you get by setting phi equal to constant. So you cut this with this horizontal plane. Isn't it neat what MATLAB can do? I love this. And Octave, if you download that, there's the same things as MATLAB these days. You can also plot this in Octave. It's pretty much the same language and it's free. That free download you might try. Takes a while to pick up the language, but that's what I plotted this in. And the intersection of the level of the plane, horizontal plane z equals 0, with the function phi gives you these two level curves, phi equals 0. And if phi equals 0 also satisfies the initial value, then these, one of these, will contain the initial value here, and one of these level curves will be then your solution curve. On parts of it where y is a differentiable function of x. So that's what you're doing here. You have an equation that can be written as d phi equals 0. You integrate it, you get phi equals a constant. Anytime you got this with a plane, that's a phi equals constant. The curves of intersection are phi equals constant curves, and along the differentiable portions of those, y is a function of x, you get solutions. When you pick the one that goes through the initial value, then you have a solution to your initial value problem. Kind of nice pictures for this section. So if we apply the initial condition to this last example, y of 3 equals 12, suppose that's our initial condition. Then we put 12 equals, what was it, x times y plus or minus this square root. And when you solve this for c, you get c equals minus 9. And so when you put in c equals minus 9, this is the unique solution to your differential equation together with this initial condition. And then you can plot it up nicely and see it looks like one of those. This is on the level curve z equals minus 9, so actually it's not the one that's shown here. You plot it way down here, z equals minus 9, and when you intersect it down there, you'd see your solution curve to this initial value problem. All right, thought I'd point out that you can find the interval of solution sometimes in your calculator. This is a hard one to find, right? What is the interval of solution for this? Well, you want this argument of the square root to be non-negative. So you have to solve where is this equal to 0. This is kind of a hard problem, right? You have to solve a cubic equation. Minus 2/3 x cubed plus 4x squared plus 18 equals 0. Where that changes from 0 to negative, the solution stops. Where is that? How do you find that? You can go on your calculator and use the solve command. Solve 4 times x squared minus 2 times x cubed plus 18. This is on a TI-89 calculator, equals 0, comma x. This solves this equation in x with respect to x. And you find out that x equals 6.6167 is where this is equal to 0. You want the side of this point where it's equal to 0 that makes this the argument positive, and it comes out to be x less than 6.6167. Is the intervally unique solution to this problem. That's where this is a differentiable function of x and satisfies phi equals c. How about that? There's the plot. That's what our solution looks like. All right. Fun. I think this is kind of a beautiful section. What I'd like to do is the integrating factors section is the next thing. And the problem with most of us is we really don't get lucky in life, right? You know, not very many people get lucky. So if you're not in the lucky crowd, what can you do to apply this technique to another differential equation? Sometimes you can multiply through by a right function and make it exact. That function that you multiply through by to make an equation exact is called an integrating factor, and that'll be the next topic. We don't actually have to always get lucky for this method to work. Sometimes we can make it work, right? And that'll be the next section we'll do next time because it's too much for today, even though it's all one section.